Okay, in that case, I'm actually going to start now. All right, before we do anything chemistry related, we're going to start off with a small math detour. Because this is very simple math, which is quite relevant to what we're doing. You've probably done this many times in, I don't know, grade 2, 3. So, okay, you have two baskets, all right? And in these, you have two baskets. In one of the baskets, you have some balls, okay? And then you have some balls in the other basket. Actually, I should use some color chalk so you can see that the baskets are different. Let's do...
Are those your chalk?
Yes.
Whoa.
They're actually quite cheap. Of course, only if you buy it in the physics building. The physics building is the only place where you buy things. I can't see what you're saying. Okay, see it. Okay, you have two baskets. And suppose you have four guys in this one and 5 things in this one. And suppose in each of the baskets, all of the balls are different. And then suppose you're first picking balls out of this one, and then you're picking balls out of the other one. We have the following question. How many balls can you, how many pairs of balls can you pick total? All right? Well, simple question, right? For this ball, I can form how many? 1, 2, 3, 4, 5 pairs, right? 1, 2, 3, 4, 5 pairs. For this ball, I can also form 1, 2, 3, 4, 5 pairs. And actually, there's a line here. And so on and so forth. So for each of these balls, I have 5 pairs, right? So I have, then how many? I have 5 plus 5 plus 5 plus 5, which, if you can notice, obviously is 4 times 5. Because I have 4 balls here, 5 balls here. So for each of the balls here, I have 5 possible options here. Okay? So I have 4 times 5 possible pairs that I can make. All right, now let's do a more general case. This should now be obvious. If I have n balls in this one and m balls in this one, then I can make n times m pairs. Okay, does this make sense? Very easy. Very true. Okay. Now let's consider the other problem, where you have only one bag, and you keep picking balls out of this same bag, right? And once you've picked a ball, you can't use it anymore. Okay, so, let's start. Okay, thank you. So, but why? Okay, sure. All right. Suppose we first. So how many? Okay. Let's suppose the following thing. Suppose we have 5 balls in here, and then we are trying to pick 3 balls out of this bag, and then each time we pick a ball, we remove it completely. All right, how many possible combinations of 3 balls can we pick out of this ball with, out of this bag with 5 balls? All right, so let's. So we're choosing 3 balls, and for the first choice we make for the first ball, right? We have 5 options. Right, so we have 5 options. And suppose we chose one of those 5. Suppose we chose this one. After we've chosen this one, we have 1, 2, 3, 4 other options. So 4. So we have 5 times 4 options already. And for the next one, we've crossed this one out. Then suppose we've chosen this one, we've crossed this one out. For this one, we have 1, 2, 3 options, so times 3. So we have 5 times 4 times 3 possible options if we're choosing, 3 balls out of 5 in this bag. Right? Straightforward. Make sense? No questions. Okay. Now, let's suppose the following thing. Suppose we have the same thing, but we have n balls in here, n total, and we're choosing k out of them. Right? We're choosing k balls out of n. Does that make sense? So here we chose 3 out of 5 balls in total. So that was 5, 3. Now we're just choosing k out of a total of n balls. Well, in this case, we can notice that we have the same pattern. Suppose this is there's like k spots that I have here, right? K spots. And then for the first choice, I have n balls. For the next choice, I have n minus 1 balls, right? And so on and so forth until I get n minus k plus 1. Okay, and then I'd multiply all of these together to get the total possible number of combinations I can get of k balls out of n balls. Does that make sense? Now, suppose we have this same problem where you have two baskets, but now we're doing it differently. Now we're going to first choose k balls out of the first basket, and then p balls out of the second basket. And this problem is like just putting the two together, right? We're going to take this multiplication, right, for how many ways we can pick balls out of this basket, and multiply it by m times m minus 1 times dot 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 times m minus, I said it's p, minus p plus 1. And then we're going to multiply this product by this product to get the total number of possible things I could, total possible number of combinations of balls I could pick first, like k balls out of this bag and then p balls out of this bag. Okay, does this make sense? What just happened? Yes? No? Okay, nods? Lindsay? Okay, good. All right, so that was the small math detour. Now that we know all of the math that you will ever need to know, yeah, no, I mean, like, just have the general idea of what's happening. Okay, so last time we looked at energetics, and what did we say energetics was? How did we think of it? We said that we have these, like chemicals have these states where you just have some atoms and they have some configuration. And then a chemical reaction takes us from one configuration of atoms to another configuration of atoms, right? That's what we said. And we said that this chemical reaction is characterized by some change in energy, right? But in this sense, we really talked about like the initial state and the state after what happened. And then we just said everything that happens in between is just work being done. And we just explained it with a single number. Now, yeah, so we were really only interested in the before case and the after case. Now, that's, we didn't really think about what actually happens during the reaction, right? So, now let's see, like most of today is us trying to figure out, well, what really happens during a reaction. Because we've already talked about the before and after cases in energetics, and we're going to talk about what happens during the reaction. And to do this, we first need to kind of think about what is a reaction to begin with. How does it look like? And there's different theories, whatever, on this. We're going to look at one of the most simple ones. And first, let's come up with some ground rules, quote unquote, of what's happening. All right. We're going to think of a reaction. Reactions happen. Like, actually, no. Let's first think of what we already know about reactions. We know that reactions from, I don't know, grade 10, grade 9, whatever it is, intuition, that reaction is either bonds breaking or bonds forming. Or bonds forming. In like a very vague sense.
Wait, what's this lesson called?
Chemical kinetics. I should probably say that. Yeah, chemical kinetics. You either have bonds breaking or bonds forming. So either you have something and you want to break it apart into two things or more, or you have something and you want to like clump two things together, right? That's kind of the two things. We either want to split something or we want to push two things together. Okay, I don't think you can see the edge of that board all that well. Okay, now it's better. My bad. And in this case, we're going to think of it in the following way. Think of all molecules and whatnot as just tiny balls, and they're flying around, and then they collide. So we're just going to think of reactions as things colliding. Things react by colliding. That's step one. Things react by colliding. Now that's the first step. Step two. Let's think about this whole bonds breaking, bonds forming. Suppose you want to break something. And suppose you wanted to break like a piece of metal, just snap it in half. Do you think you can do that? Probably not, because you're just physically not strong enough. And we can use that intuition for chemical reactions as well. If you think of two particles, for them to actually for one to collide into the other so that one of them breaks, it needs to hit hard enough so that it actually does break, right? So that's one thing. And if you have bonds forming, that means you have two things flying into each other and you want them to still stick. Now imagine you have to take two metal bars and slap them together so that they stick. It's definitely possible, but you're going to need to put in a lot of effort to do that. So we get the following thing, that particles, so for a reaction to be successful, to be successful, is that, I don't know how you spell it. Is there one L or two? One L, probably. I don't know. Is it one L or two L? Successful. There should be two.
I think you missed an S. Unless it
That's an S.
says.
E.
What's the F?
F.
Oh.
That's Fs. So these are my Fs. Like the music F.
I thought there's two S's.
Yeah, okay. No, you get what I said. I said it out loud. I don't know. Something. And erase it so it's both right and wrong at the same
I'll
time.
write it.
Reaction to be successful, particles need to fly into each other fast enough. Particles need to be fast enough. I can try and write print if you guys like. Fast enough, right arrow. Therefore, they need to have sufficient kinetic energy. Would people prefer I write print? I can try and write print.
No,
Sufficient
Bro, I hate my eraser.
kinetic energy.
What the heck?
Okay, so we already have two conditions. First of all, we're thinking of, okay, particles are just these things flying around, smashing into each other. Second thing, they need to fly fast enough for something to actually happen. Because, they can just fly into each other and bounce back and nothing happens. Okay, does that make sense so far? Let's see if I can lift this.
Whoa.
Wow, okay, hopefully that doesn't fall down.
That would not stay up there.
Magic. It's U of T magic. Okay, that's two.
How is it like a movie from there?
Yeah, okay. Actually, I still need that. There's still a little bit of space. They need sufficient kinetic energy. Now, what do we remember affects kinetic energy? What kind of is a measure of kinetic energy from the last time we talked about?
Temperature.
Temperature, exactly. So now we know that temperature,
Ouch. I'm not having a good day, guys.
is relevant to how well things react. Now we know this fact. It's kind of obvious, right? But now we kind of know why. And we can imagine that at higher temperatures things would probably react better because things are generally going faster, so they're better at breaking and sticking together. That's one thing. The other thing, this kind of starts to explain the whole activation energy thing. Remember when we had those energy diagrams and we said that if you start off at some energy, you need to go a little bit above the actual energy you're going to end up at? Well, this is kind of it. You need a certain energy for you to collide successfully so that you either break apart the other thing or that they stick together. And you need that to happen, but after that you don't need all of that energy all of a sudden, so you're going to go back down in energy. And I think for those of you who did physics, you remember that if you have a, what are they called? Inelastic collision, where things stick together at the end, your energy is not conserved. And that's kind of, yeah, exactly. The concept bomb is conservation of momentum.
Mom.
Yes, that's momentum.
I
And
don't
then-
know, I didn't take physics with like
Okay, well, that's one thing. Okay, so this should be okay. Now let's come up with more conditions. And now we're going to remember something called Vesper. And the only thing you have to remember about it is that things aren't actually balls. It's like they can be branched out and you have like different bonds and different things, right? Does that make sense? Like you can have chemicals which, I don't know, they like look weird, something like this. You have, I don't know, carbons or something. And the issue with this is, well, what if for my reaction, I want to specifically break this bond and not any of the other ones, right? So that means I want my other particle to hit something that's like here and not here. Because if it hits something here, it's not what I wanted to break off, right? So what we get is that we get our third condition. We get the idea that, so from Vesper, we can guess that the geometry, is this large enough for people to see?
Yeah.
The geometry of particles, of molecules / of reactants, also affects how well the reaction goes. The reaction goes. All right. Now, now we're going to look at the, right, this doesn't lift. Okay, good. Now we're going to look at the last thing, 4. And think about the number of particles. Does the number of particles itself affect how well the reaction goes? Well, think of 2 cases. Suppose in both cases, like you have some reaction, and in both cases you have the same amount of reactants, right? But in the first case, we have like a room this large, and all of these reactants are in a room this large, right? Just spread out. And then in the second case, you have like a small water bottle like this, and you cram all of the reactants in the small bottle like this. Where do you think the reaction will happen faster / is more like 2 particles are more likely to react?
Definitely in here.
Okay. Well, the answer is it's going to be it's going to work better in the smaller space, simply because if like things are confined into a smaller space, there's a higher likelihood that things will actually collide because they're just closer to each other, right? Like if you are if you're in an elevator with 10 people versus in a room with 10 people, like what is like in the elevator you're more likely to step on someone else's foot than in a large room. Though it does happen. Some people can do both in both cases. And
some people are that
we avoid them.
crazy.
Yeah, we avoid them. Okay. Don't be that person. So what does this imply? This implies that concentration of reactants, affects how well
Everything's going wrong.
the reaction proceeds. These floors were probably not cleaned since, I don't know, 20 years ago, so.
Doesn't matter if I drop my chocolate chip.
Probably don't leave it there.
I
Definitely.
can't find it. I lost the chocolate chip.
Guys,
It was an accident.
Okay, we'll go on a scavenger hunt for your
Yeah.
just try not to step on it. Okay. Because I'm not sure how.
No, I know.
I don't
that's
think
why
we're
I'm
allowed
so-
food in here.
That's why I'm so.
So like, you know, drinks are fine, but that may be put away. Okay, now think of what could affect. Okay, what did they say? Yes, concentration affects reaction. So okay, now we have. Actually, I'll keep this up so we always have this. Okay.
Oh.
Okay, that's. This one's a little bit too late. I don't like that. Okay. So now we have 4 conditions. 1, 2, 3, 4 that we need to satisfy. Okay, so far we've just kind of been exploring things without having a specific question in front of us that we're trying to answer. Well, let's write down this question. I'm not even visible when I go into the corner like that. Like that. Okay, is that better? Yeah. Okay. So we have the following idea. What was I saying? Right. Let's now pose a question in front of ourselves. So we aren't just like blindly finding stuff that's true, but actually trying to answer a specific question. And in industry, you have like a large factory and it's producing this chemical through some chemical reaction. A key important question for them isn't just about how much we're going to produce in the end, but how long is it going to take us to produce that amount, right? Because maybe they'd rather produce less, but they produce it faster, versus you produce a lot, but it's going to react in 10 years. Because there are some chemical reactions which are that slow, I'm guessing, but there should be. So now we have the following question. Well, can we predict how fast a chemical reaction happens? A chemical reaction proceeds. And in other words, can we find an equation for how fast? So instead of this, can we find an equation that describes how fast an equation for how fast the chemical reaction proceeds? Okay, well, can we find an equation for how fast the chemical reaction proceeds? That's what kind of equation does it have to be? What kind of equation, what is it that we need to find that tells us how fast something goes? And from calculus, you're going to remember that that is the rate of something, right? So we are going to set on a quest to find the rate of reaction. Rate of reaction. And how will we define this? So it's a little bit more clear what I mean by how fast a reaction proceeds. The rate of reaction is either how much reactant is used up every second, or how much product is made every second. So how much product / reactant is made / used per second. Does this question make sense so far? Why we're asking this question, why this question is relevant to us. Okay. I would also like to remind you, if you guys didn't check up on what derivatives are and so on and so forth. Suppose you had a graph of how much reactant you do have, so reactant, at a point in time. So it would look something like, I don't know, something like this. Suppose you had a graph like this, and you can say that, okay, at 0 time, I had this much reactant, like, I don't know, 3 moles, and then after like 5 seconds, had 1 mole of it left. Okay, does that make sense, right? You're going to remember from calculus that the tangent to this, the slope of the tangent to this point is the rate of reaction at 5 seconds. So the slope of this line is the rate of reaction. Of this line.
Wait, what is it?
The what?
What is this? The one on the left label?
Reactant.
Oh.
Like how much of it you have in moles.
Oh, okay.
That's this axis. And then the slope of this line is your rate of reaction. Okay. Does this make sense? Why that's the rate of reaction for the slope, so on and so forth? People more or less remember vaguely the calculus they learned last year. Right? Okay. I don't want to erase that. I don't want to erase anything as of the moment, actually. I have like a Oh wait, I can lift this. There is another board behind it. Perfect.
Wow.
Okay, then I don't have to erase anything at all. Actually, no, I'm not gonna erase this then. I'm gonna lift this board. Wait. Okay. Perfect. Okay. So that's great. We are now answering a specific question. Now, one of the things that we figured out that like how successful a reaction is depends on all these 1, 2, 3, 4 things. It depends on the energy, so the temperature. It depends on the geometry of how the reaction is colliding. It depends on the concentration. And I mean, we think of things as just like balls flying around, colliding into each other, but these balls also have geometry. Okay, cool. So ideally, our equation that we find for the rate of reaction is going to have to be able to answer to all of these 1, 2, 3, 4 criteria, right? It's going to have to account for them. Well, the way we account for them is going to be a little bit sketchy. And you know, 1, 2, 3, so energy and geometry are quite like, it's a little bit not obvious how we have to account for them. But the last one, how we account for concentration, is going to be quite obvious in a second. That's the easy one. So we're going to start off with dealing with that one first. And now we're going to think, I'm going to introduce a specific reaction to kind of help us move along with this question. Okay. We're going to consider the following chemical reaction. It's a general chemical reaction. You have n particles of A, and then you have n particles of B,
Oh, this is where the math is.
and then you get what? You get, but yes, you're right. You get this thing, and they all stick together. You have n particles of A, n particles of B, and then they all stick together to form this AMBN, right? And we're going to, yeah.
Just to confirm, we're counting the concentration.
Right now, we're just talking about number of particles. For now, we're going to move on to concentration later. It's just easier to first explain the particles, and then we'll do its concentrations. Okay, so we have this chemical reaction, right? This makes sense. What's that? And A and B is like something arbitrary. And think of all of these particles just collide in one spot, and they all stick together, right? Okay. Now, the proposed method of finding an equation for how much product reactant actually successfully reacts per second, I'm going to suggest the following approach. We're going to find, well, how many collisions possibly can happen, like in general? How many collisions actually can possibly happen? And then we're going to take this number, we calculate how many collisions can possibly happen, we take this number, and then we multiply it by the percent that actually successfully happens. Okay? And then take percent that successfully happens. That successfully happened. Okay, does that make sense? What approach we're taking here? We're going to look at all of the possible things that could collide and all of the possible combinations. And we're going to take the percentage of those that actually successfully happen. All right, well, now this comes back to this whole math detour bags problem. Because what are we doing? We have some number of particles of particles A, and they're in one bag. And then we have, I'm going to use different letters for this now. So let's say we have, actually, let's say that square brackets of A is the, you guys learned what the square bracket notation means in chemistry yet? Concentration, yes. Do you guys, kids. Just pretend it doesn't mean concentration right now. Pretend this means just the number of particles of A, like in moles or something. Number of, actually no, just in ones, in like single particles, not even in moles. Number of particles of A, and then B is number of particles of B. Do you agree? Okay, so this has A particles, and this has square bracket B particles. And what are we trying to do? We're trying to choose a single collision needs what? A single collision needs M particles of A and N particles of B. Do you agree? So each collision is equivalent to us first choosing M particles out of this bag, and then N particles out of this bag, and then N particles out of this bag. Do you agree? Okay, so in this case, let's write down the equation for the total number of such combinations that we could make. Right? Let's write down the equation for the total number of ways we can pick particles so that we have M particles colliding and N particles of B colliding. Okay, well it's going to be exactly this same equation. I'm just going to rewrite it in like this kind of notation. Let's see, how many ways can we pick M particles of A? We can pick them in, so we have A first, right? Then we used up one particle, we have A minus 1, right? Then dot 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 times A particles minus M plus 1. Do you agree?
This is how many combinations?
This is how many ways I can choose M particles, MA particles. If I have A particles of A total, like A square brackets particles of A total, how many ways can I choose M particles out of this bag? Does that make sense? Okay. And now let's choose particles of B. So we're going to multiply this, carry over the multiplication sign, by B times the number of particles of B minus 1, dot dot dot, the number of particles of B minus N plus 1. And we're multiplying all of this together. Do you agree? Now, what's one thing we can notice? Generally, the number of particles that you have is like an insanely huge number, right? Because moles is like what, 6 times 10 to the 23, right? 10 to the 23 particles. 10 to the 23 minus 1 is still 10 to the 23. That minus 1 isn't going to do anything, right? And we're going to assume that M is like a couple particles, not like a billion particles colliding all together at once, because that's just never going to happen. And even if they did, like for all of them to stick together, it's too much energy. So okay, we can say that A minus, we can say that A minus, the number of particles of A minus some number, I don't know, C, is really just approximately A. We can kind of say that, right? Because like a million minus 1 is still more or less a million. And in this case, you don't have a million, you have like millions of millions of millions of millions. Is that 6? I said it 4 times, right? So that's 10 to the 20%, close enough. So then we can say that this is approximately equal to A to the number of particles of A to the power of M times the number of particles of B to the power of N. Do you agree? Because I have M of these brackets, right? And it's plus 1 because this one has like nothing in front of it. So it's 1, 2, 3, 4, and like up to, there's M of these. Does that make, do people see why there's M of these and why there's a plus 1 at the end? Because if we had A minus M, that means we've already selected M out of the bag, right? But once we've already selected M out of the bag, we don't need to choose more. So we stop at choosing like plus 1, the last particle that we pick up. That's our last choice. That's why we have a plus 1 here. Okay, does that part make sense? Does it make sense what this meant? Does it make sense how we got from here to here?
Wait, sorry, what does the equation represent?
This equation?
Yeah.
This equation is the total number of ways that you could pick M particles of A and then N particles of B. And physically in our chemical reaction, it represents how many possible combinations I could make of particles that would potentially give us a reaction, right? Because to react, you need like the bare minimum for this reaction to happen. You at least need the right number of particles, and we find out that we can get this number of particles in this many ways. There's this many possible combinations that could potentially end up in a successful reaction, right? So this is the total number of all of the things that could happen in a second. That definitely doesn't mean that everything reacts with everything in 1 second. So this is us completing step 1. How many collisions can possibly happen at all? And now we want to take the percentage that actually successfully happen. Okay, well, do we know how to take this percentage? As of the moment. Do we know how to take this percentage? How to figure out which ones of these are actually successful? No, we don't. Because we just don't. And now we engage in something that is quite poor physics, but excellent chemistry. And we say, hey, let this percentage be some number k, some arbitrary number k. And we're going to say that our rate of reaction is k, which is our percentage, which we don't know, but we'll find it out from experiment. And we never need to bother about what this number actually means theoretically and how you arrive at it. So we're just going to take the total number of possible valid collisions, a to the m times b to the n, and multiply it by some arbitrary factor, which we will find out somehow later and worry about it later, and say that's the number of collisions that actually do happen per second. And this is our rate law for this reaction. Yes?
Oh, we were just apologizing.
Oh, okay.
I
I thought you meant like, sorry, like you have a question. Okay, all of this makes sense so far. You should write this down because this equation is the most important out of like all of it. Because this is like the next like 4 months of your course, just this equation. Right, K is this percentage. K is the percentage. So let me write it like this. Fortunately, this board is not liftable. So this K, this A times B to these powers is the number of possible combinations of particles that could react, that could give you a successful reaction. Number of possible collisions that could result in a reaction. Result in a reaction. Right? This is like everything that could happen. And then K is the percent that does happen, that does successfully happen.
It's just a random constant that they came up with.
Oh no, that's like most of engineering and everything. It's like, oh, we don't know how this works. So let's just say like there's some constant and it works. And then we can figure out this constant by doing some experiments. And then you hope it does actually work the way it does. And it turns out it does. It's magical.
Is it the same for everything?
What's the same? The constant? You don't know the constant. The constant, oh yes, this is a good question. So remember how we said this equation has to account for energy, it has to account for concentration, and it has to account for geometry, right? This part accounts for concentration, but we have so far not accounted for the geometry of the reaction, how things have to collide, and for the energy of the reaction, how fast things have to collide. So we're going to claim that this constant also takes care of the issues with, it considers how many particles will have enough energy to collide, And we're going to also suppose that it will take care of like how exactly the geometry of the collisions has to be. And because of this, this constant therefore is now different for every different temperature and for every different reaction. So for any reaction at every temperature, you have to find this constant experimentally.
Wait, this takes care of 2, 3.
This takes care of 2 and 3. And then this kind of takes care of 1 and 4. So this is geometry and energy. Like how many of all of these possible total collisions will actually, after colliding, have a successful, like the right geometry and enough energy to successfully react after the collision. Yes?
Is K kind of similar to like the yield rate for every temperature?
I think so, kind of. Just like, I don't remember what the yield rate is to begin with. All I can tell you, K represents the percentage of, out of all the possible reactions, which ones actually do happen, and which one after a collision actually do successfully like stick together or break apart or whatever it is. Okay.
Wait, what does R represent?
R is the rate of reaction.
Oh.
So we're saying how much stuff reacts every second is the total number of possible things that could react and collide, potentially, times the percentage that, like, taking the percentage of the ones that actually do successfully collide. And this percentage is different for every reaction at every different temperature, and we are just gonna have to like find it out somehow magically. Okay, getting Instagram DMs. Cool. Does this logic make sense? Because this is like really important if you understand what every part of this equation does, what every part of it means. Yes? No? Does it make sense how we arrived that this is in fact the total number of possible collisions? Yes? Okay, does this make sense how we magically came up with this constant and said, let's hope it fixes all our problems? Like there's no logic to this. We just say, let's hope there is a thing that, a percentage that does this. And then this is the rate of reaction. Okay. But so far, what we've been doing is a little bit inconvenient. I think I can erase this now, because we've somewhat answered this question.
I've had enough.
Actually, you know what I could do? Instead of keeping there every time I switch boards, I could like move the camera around so it's easy, because I don't need the charging like 24/7. I can do something like that. Okay, there we go. So this is the next thing. Doesn't erase all that one. So far, we've said what? Actually, yeah, I lied. This doesn't yet deal with concentration.
Oh.
Why? Because these so far are the numbers of total numbers of particles we have. We don't have anything in this equation. Is that visible? Yes. We don't have anything in that equation so far that actually tells us how these particles are spaced apart relative to each other, right? But what does? Concentration does tell us, right? So we have to fix this equation, fix the equation. Sorry, so I lied. So far this equation only accounts for number 1, the fact that things react by colliding.
What about the other two?
The other 2, that's the constant, right? The 2 and 3 is the constant. So this takes care of the fact that things react by colliding, and we're going to make it also account for concentration, but that's later. And then we say that this constant magically accounts for geometry and collision. Sorry, I misspoke. I went ahead of what I was doing. Right? So now fix the equation to account for concentration. Concentration. Okay. Now, suppose we have, like, I don't know, some very large beaker. And it has our, okay, I left these here. And it has our 2 reactants, A and B. Suppose I used green for B and yellow for, okay, I'm just gonna, 2 reactants, red and whatnot, and suppose this is like distributed quite randomly, right? This is distributed quite randomly, and it's like evenly spread out. All the particles are evenly spread out, right? If all of the particles are evenly spread out, then, okay, let's see. If all the particles are evenly spread out, let's split this beaker into like boxes of even shapes, right? Let's split our beaker into this, and suppose you have like the same number of particles of each kind in each one of these boxes. Okay, so it's like kind of the same. I'm gonna do like two of each in each one. Assuming that everything is evenly spread out, more or less, we'd expect that what happens in each one of these quadrants is going to be the same, right? Vaguely. If it's like evenly mixed, you'd expect what happens locally is what happens locally everywhere. So in that case, instead of talking about everything that's happening in the entire thing, we can say, hey, how about we just look about what the stuff that happens in a single liter, right? And just, if we know what happens in a single liter, we know what happens in 2 liters and in 3 liters. Because we'll just know the exact same thing is going to happen, it's just that, and it's all going to react at the same speed, but it's just going to be more product in the end, right? Because, I mean, it should be just symmetrical like that. Plus, you can always change your units of volume and just consider this like everything as one whole beaker. So we're going to make the following assumption. Is that the rate of the speed at which things react, not the rate exactly, the speed of reaction in 1 liter of the whole thing, of the whole beaker, is the same in quotes, is the same as in 1 liter of it. So what I'm saying is, in 1 liter you're going to have less things react, but if you take the rate of reaction of like how many things react here per second, multiply it by the total volume, then you'll get the rate of reaction of the entire thing, is what I'm saying.
Chi-squared test.
Pardon?
Oh, it's a biology.
Oh yeah, I've heard of that. It's something. I remember I went to like a colloquium or something.
Connection.
Yeah, but it's not. I don't. It's kind of. Let me think about what I remember from like 5 minutes of listening about it.
I don't want to know about it.
It's kind of. I don't know. Okay, so does it make sense what assumption we're making? We're saying that if we look at what happens in 1 liter and then multiply it by the total number of liters, then we're going to get what happens overall. If we take our entire reaction and we look, no, we're looking at. Sorry, I should speed of the beaker is it's not the same. Sorry, this is a poor way of phrasing it. I'll say it. I won't write it down because it's too long to write it down.
Okay.
If we take our entire beaker, right, and say our entire beaker has like 5 liters of reactants, 5 liters of reactants, and they're evenly mixed. If we split everything into like with this beaker into 5 separate liters, and we look at the rate of reaction in 1 liter, so how many particles successfully collide in 1 liter, right? Then if we multiply that number by 5, we're going to get the total number of particles that collide in the whole thing successfully. Does that make sense, what I just said? So now instead of looking at the entire thing, we just care about what happens in 1 single liter, and then if we know the volume, we can just multiply and get the answer. Yes?
Okay.
Did that make sense?
Yeah, but I have no way of phrasing that now.
Well, you can just copy what I said. But, yeah.
Wait, so does that mean
I'm
the
gonna
speed
talk
is
about
like
iris
a
back.
factor?
Pardon?
The speed is like a factor
Of the what?
factor of the iris.
Yes, but we're about to rephrase our question, so we don't care about that. We're about to change our question. Okay, I'm gonna give you guys a second if you have anything else to write down. I've been confusing because I didn't prep this part like explicitly of how exactly I'm gonna say it. I thought I figured out straight away. I did eventually, but it took me a while. Oh, 23.6, that's nice. Oh, there's a thermostat I can like. Okay.
Did you ever go? Yeah. Oh, you did.
Okay. That's all recorded there, guys. Okay. Am I good to continue? If you say yeah, no one else doesn't know. Okay. So now we can start rephrasing our question. Before we said, okay, let the rates be the total number of particles that collide in the entire thing per second, right? Now we're going to redefine the rate. So actually, you know what? Assumption? Okay, wait. Actually, I'm going to write this down for you guys. Actually, I think I can say it.
Damn it.
If we have reactants in volume V, number of things, number of successful collisions, collisions in entire volume is equal to the volume times the number of collisions of successful collisions. I don't know how you spell successful. Still, successful collisions in 1 liter. I have like a bad habit of like using up chalk and like even when there's like this much left, I still use it. But then I get tired of it and I just crush it. Okay, is there a longer?
What's the number of successful collisions in
So number of successful collisions in the entire. If you have
Yeah,
think
so-
of volume V, number of successful
Shouldn't it
collisions
be
in
the
the entire
number
thing.
of, oh, is V in liters?
V in liters. Yes, V in liters. In 1 liter. So the number of successful collisions in the entire thing is the number of successful collisions in 1 liter times V.
Oh.
That's all I've been saying for the last like 10 minutes.
Damn.
Sorry, I'm just slow figuring out how to say things. Okay, we're gonna probably take a break in like 20 minutes and then go get lunch or something.
Yeah, I need to stop spending money.
My eraser is broken.
I'm just
You're falling apart in every possible way. Okay. So now what do we get? Now we get that if we know the volume, and it's quite easy to find the volume, right? If we know the volume, then it's just enough for us to care about the number of successful collisions in a single liter, right? Yes, does that make sense? So now let's take this equation and restrict everything to 1 liter, right? So the number of particles of A in 1 liter, number of particles of B in 1 liter, and the rate of reaction in 1 liter, right? What is the number of particles of A in 1 liter? That is the concentration of A, right? So because of this, if we know V, then we don't need to find out the total number of things that successfully collided. It's just enough for us to know the number of successful collisions in a single liter, right? So we're now going to focus our attention on that and convert this equation. It's actually called the rate law. But you don't have to write that down right now. We'll write that down later. So we can convert this equation now into everything happening in a single liter. Okay. So now we're going to redefine a bunch of things. R is now going to be the, actually wait, now, give me a second. We're going to first redefine A and B, AB, to be the concentrations of A and B. Of A and of B. In the entire thing, right? Because that's going to tell us how much of A I have in 1 liter, how much of B I have in 1 liter. Does that make sense? So now, this and this is the concentrations of A and B. Does that make sense? K still stays the same because it's a percentage, right? Percentages don't matter. And now, what do we get? We get that R is now the number of successful collisions in a single liter, right? Number of successful collisions in a single liter. So R is number of successful collisions in 1 liter. Don't ask me. I've probably spelled it like 5 different times today. I'm not here to tell you about spelling, I don't know about it. But I don't think I'd be tested you on spelling, so that's good. Teachers just judge you silently. But then they misspell things even worse than you ever have.
exactly.
So then you don't feel bad. Once again, that was recorded.
It's okay.
You be careful with what you say. Okay, number of collisions in 1 liter. Now, what exactly does the fact that this is a 1 collision in a liter mean about graphs?
Wait, there's so
Oh
many.
wait, we got the whole chocolate chip debacle. Never mind, sorry, go ahead.
Okay, so what does this mean? What does this mean
So many.
about the actual physical situation that it's now the rate of reaction per liter? If before we said that the rate of reaction is the tangent to the graph where this is like the number of reactant in moles, in moles, and we said it looks something like this, and then at this point this would be this tangent, the slope of this tangent line is the rate of reaction. Now we're saying forget about this. Now we're saying if I had the graph of concentration of reactants, at a specific time, right? And that's probably going to look something like this, right? Now R is the slope to this new graph. And then the slope of this line is now R. Is R. So now R has become rate of change of the concentration of reactants. Not the number of molecules of reactants, but the rate of change of their concentration. So we're going to define R as the rate of change of the concentration of products or reactants. Okay, and we still get that it's the exact same equation. We've just relabeled everything, where now everything's now in terms of concentration. This is the concentration of A, this is the concentration of B, and R is the rate of change of the concentration of one of them. It depends. We'll get to that a little bit later. Okay. This is like a stopping point. We finally derived the rate law. You can now label this as the rate law. It's quite important. And we can take a break. Questions? I'll give you a second to write stuff down. This was, only 59 minutes, week. Okay. I'm slow. It took me this long to say all of this. But yeah, I should have, I made a mistake here, and then I made a mistake Two mistakes.
We define R two separate ways.
Yes, but forget the old definition of R. This is the new shiny one. Forget the old one. The old one was like as a stepping stool for the new one.
On the other board, like the one that you just lifted up, we define R as the number of successful collisions in 1 liter.
Yes, but that's the same thing.
Oh.
Because the number of successful collisions per second in 1 liter is the same as how
it's the
fast
same
concentration
for
is changing in a liter.
Okay.
Because you're just dividing by 1 liter and dividing by 1 is still the same number. Actually, what did I say to you? The number of successful collisions in 1 liter per second. Sorry, I forgot to say. Per second. The number of successful collisions in 1 liter per second is the same as the rate of change of concentration of products or reactants. Yeah, they're the same by definition.
Okay, so we have our final equation.
Yes, and this is the final equation where this is concentration, and this is the rate of change of concentration. And see how it's the exact same equation as we had with like the number of total number of particles, but now this equation actually accounts for how well spaced they are to each other. Versus before, when this was just the numbers of particles we have the total, it didn't. So this is a vast improvement on what we had before, because it accounts for more stuff, and is probably more correct. Oh, everything is mirrored. I'm gonna have to flip this video. Okay, I've said this. Did I forget anything? Yes. Okay, actually, I'm gonna say one small little other thing, and then we'll stop. So I said that the temperature affects the rate of reaction, right? So we can increase our temperature or decrease our temperature, right? And we said the concentration affects the rate of reaction as well, because if things are closer together, then you have more collisions, because it's like higher chances that someone's going to step on someone else's foot. However, we have the following issue. What about this piece of chalk? What if I want to react, just dip this piece of chalk in, I don't know, if I dip it in acid, something should happen, right? If I dip this piece of chalk in acid, this piece of chalk, I'm going to have am I good to erase this? Did people understand what happened on this board?
Guess so.
Okay. Guess so. Actually, I'm just gonna erase this, because this is like now wrong. We're relabeled our old notation. It's actually probably a bad habit, but I was just trying to show you that it's like the same idea. Okay. Suppose I have a beaker with acid, and I dipped my piece of chalk in acid. This is my piece of chalk. And can we really apply this law to this situation? No, because this chalk doesn't really have, it's not evenly spread apart.
Surface area.
Yes, exactly. This is where surface area and things come in. So this thing only works for stuff that like is evenly mixed. Only works in that case. In this case, we don't really have an equation, at least in high school. Maybe there is, I don't know. Normally what you do, ideally, you can take the chalk, you first crush it up into a powder, mix it with like water or something, and then pour it in, and then you can have like a concentration of that chalk. That's like an easy way to get around it experimentally, and then you can apply this equation. However, if you just dip this chalk, what would affect its rate of reaction? Well, like you said, it's really just surface area. If there's more of the chalk exposed, then it will react faster because more of it is available to react physically. So yeah, that's kind of the whole point. Now the key important thing with this is being able to draw graphs. That's what you guys are going to be tested on. And this is perfect. Yes. So in a liter. In 1 liter, that doesn't successfully happen now in 1 liter. Actually, can you guys see this board? Jocelyn, can you see this board? Okay. Then let's quickly translate to this board. And let's take my red and green chalks. and yellow. Okay, perfect. Probably shouldn't forget them. So suppose we have this graph of how much chalk reacts, like the concentration of reactant, right? To time, right? Suppose if I just dip this chalk in acid, the concentration looks something like this. Like it at first reacts very fast, and then it kind of levels off. Actually, why does it make sense that it first reacts really fast and then levels off? Because our rate of reaction is a product of the concentration. As the reaction goes on, the concentration decreases, right? Because stuff gets reacted. So as the reaction goes on, this number gets less. So the slope gets lower. That's why you have the fastest rate of reaction at the beginning of reaction always, and then you kind of get more flat as you go on, and then eventually you don't have any reactants left at all, and then your slope is 0. Does that make sense? How this reaction already tells us about how this graph should look like a little bit. Yeah? Okay, well, now suppose I put in the same chalk, but I first crushed it up. So this is just like normal chalk in acid. Normal chalk. Then suppose I took the chalk, I crushed it up, I mixed it with water, and then I poured that in, and like it's still the same volume, it's still the same concentration of acid. How is the graph going to look like in that case? Actually, let me redraw this so it's a little bit easier to draw the other comparison. Suppose it's like this. Okay. How would the other graph with the crushed chalk look like? How would the graph with the crushed chalk look like? Think about it. Compared to this graph. If I crush my chalk, will the reaction go faster or slower? Faster. So initially the slope is going to be faster. But I'm saying that I have the same amount of chalk still. So is it going to level off in the same, it should level off in the same place, right? So this is going to go faster, but it's going to level off here. And end up in the same place in the end. So red is crushed chalk. Do you agree? Yeah? Now, suppose I did another thing. I have the same amount of chalk as I had normal, and now I still use the same chalk, but now I throw in, the concentration of acid is less. And we still have the same volume of acid. So green is same chalk, lower concentration of acid, and same volume of acid. Same volume of acid. What's going to happen in this case? Is initially the reaction going to be faster or slower?
Same chalk.
You have the same chalk, but you have a lower concentration of acid. It's going to be slower. So it's going to start off like that, slower than normal. The question is it going to end up in the same spot? Look, you have lower concentration of acid, but then you have the same the same volume of acid. So in total, do you have the same amount of acid?
You have more chalk.
You have more chalk than you had acid. So now, am I going to be left over with the same amount of chalk as I did before?
You're gonna have more chalk.
You're gonna have more chalk left. So, wait, of the reactant, this is the concentration of chalk. And pretend it makes sense to talk about concentration of chalk for a single bit of chalk. Just coming up with a graph. Or suppose this was powder chalk and this is an even finer powder of chalk. I don't know. So normal chalk, if you have less volume, it's going to level off higher. Does that make sense? And essentially, this is one of the key things you guys get tested on in IB quite a lot, is you're given like, okay, here's a graph when this, and this happens, and now draw me a graph relative to this. If I say double the concentration of this but keep the volume the same, or double the volume and keep concentration the same, something like that. Does that vaguely make sense? Okay. And now I think I'm done talking. Ooh, as promised.